Greetings, everyone. Welcome back to further discussions of limits. Now, part 3. What we're going to do is we're going to discuss how to make a limit more precise language. We've been using limits so far with number patterns, and that's pretty good as far as everything that, for understanding and seeing what a limit is doing. But remember, in math, everything at some point needs to be 100% concrete and have some way of actually proving it for all values. We've been doing a sampling version of limits by putting numbers in charts and just kind of feeling where the patterns are going. This short lecture video, what we're going to do is put it all in concise mathematical terms that will work for every value. In other words, be a 100% solid way of proving a limit. So before we get started on that, just a little reminder from some of your algebra days. An absolute value is used as a distance measurement. So if I write the absolute value of z minus 5, then I'm talking about the distance between some value z and the value 5. And then when I put a qualifier on the other side of it right here, a comparison of some sort, either an equals or a less than or a greater than, then I'm saying where I would like that distance to go, right? So 5 is sort of like the center here because I'm saying the distance from z to 5. So z can be a whole group of numbers, okay? And I'm talking about the distance to the value 5, all right? And the way you know is whatever number can zero out this thing. Like if I plug 5 in, 5 minus 5 is 0, then that's where the center is, okay? But then I have the less than 2 here. So I'm saying the distance between any number and 5 should be less than 2. And any number that's within that description is then part of the interval, the set that I'm discussing with this statement, right? So notice here, 5 is the center, and then I went a distance of 2 on either side, and then all of the numbers, because it's less than that. So everything closer, less than the distance, anything closer to 5 is within the set that I'm talking about. And this kind of thing is used a lot in generic mathematical proofs, and that's because sometimes we need to talk about what we call a neighborhood around a value. So right here, I would also call this the neighborhood of values around z equals 5 of size 2 or of radius 2, okay? You can actually generalize this idea into 2 and 3 and higher dimensions by using circles and spheres and things like that. But here on a number line, it's just an interval, and I'm talking about all of the values on either side of 5 at a distance of 2 away, okay? All right, so keep that in mind as we go through this precise definition of limits, okay? Let's go through the words first so that we can pick it apart as we look at the graph, okay? So f is just going to be some function, right? We're just talking about a function in general. And I want it defined on an open interval. Basically, for the most part, that just means make sure that the domain has more than just, a few points in it. We're talking about a function that has whole intervals in its domain, not a function that's like a scatter plot or just a bunch of little points that are just here and there, okay? The domain needs to be a connected interval, and that interval needs to be around the point that we're interested in taking the limit towards, right? So as x approaches c, whatever that c value is the interval that I want my function's domain to be defined on, okay? So that's what we mean by let f be a function defined on an open interval. I just mean that the domain needs to be something that's all connected, and I also want it to contain the point. Now the function itself, remember, for limits, since they're gossips, right? I don't actually have to have the function defined at the point c, but it needs to be defined on all of the points in the interval around c, right? So kind of like this. It didn't have to be defined at 5, but I want it defined in some interval all around 5. Okay? Now, here's what this means. Okay? L is some real number, okay? Just some number. We're not doing the infinite ones at this point. Then the limit as x approaches c of the function is equal to L is a statement. And that statement means that if you pick any number, I'm using this symbol epsilon to represent some number. Okay, this is the typical letter that they use for this. You could really use anything, but we didn't want to get it confused with some of our normal English letters that are, thrown on graphs all the time. So, epsilon is some number that's non-negative and not 0, greater than 0, see? And delta, same thing. This lowercase d is called delta. Basically, these are just two really small numbers, okay? They're positive numbers, but typically, like with limits, you want to get really close. So we're letting them be really small numbers, okay? So in other words, if I say that some epsilon exists, then there also has to exist a delta number such that if the distance between x and c, remember we're trying to let x go to c, so the distance from x to c is less than delta, okay? Then, if that's true, then the function distance to L, the limiting value, is less than epsilon. Now I want you to visualize what this is saying by using these two different distance statements, okay? Remember, we want precise language for letting x approach some value and then letting the limit measure the y value that comes as a consequence of letting x get close to something on a function. Okay, so as x gets closer, we want the y value to scrunch in to some function value, right? And that should be the limiting value. As x gets closer, y gets closer. So we're going to look at it from the reverse. If I pick some distance that y is around the limit value, right? So pick an epsilon such that the distance of the function is less than that, pick the y first, then I can always find a delta, right? Then there exists a delta such that the distance on the x-axis is within that. And okay, so again, still think about that. That's our precise language for being able to pick up every value as x gets close, making every value as y gets close, right? We don't want to just do a quick sampling of a few numbers here and there like we were doing with the charts before. I want to make something generic that can cover all the values of x as I hone in and get closer. And as a consequence, all of the values of y getting close to that limit value. Okay? So this is the way we do that. We use distance language to talk about letting the x distance be some value that I can shrink all I want, causing the y distance to do the same thing around the limiting value L. All right, so that's what this is. Look, okay, for this graph right here, here's my function, okay? And let's say this is the point right here that we're interested in. So x equals c and y equals L are the coordinates of that point. And again, the function doesn't have to be defined there. It just is in this example, or in this pictorial here. Okay, so here's the thing. If I pick some distance called epsilon around the limit value, or the suspected limit value, remember we're trying to prove that it is that, right? If you pick some epsilon here, it's going to be high and low. That's a neighborhood, right? Like over there. That's a neighborhood around L. So that's this right here. This little interval is this. This and this are the same thing. I just used y here, but f of x is the y value, right? So this is this. Okay? So what this is saying is if I can find an epsilon, then there must exist a delta where all of this is true. So in other words, if you pick an epsilon, come back over to the function, see where it hits the x-axis, then you should always be able to find a delta, right? Such that it fits inside of this. Okay, so let's go back through. I pick an epsilon, that gives me some little range of the function, right? That gives me some little stretch of the function here, and then that comes down here to the x-axis and gives me a little section. I need to be able to find a delta inside of that section, okay? And if I can find a delta, then that epsilon is good. All right? That one epsilon, if I pick one, then I can find a delta that fits, right? You'll notice that doesn't take up the whole stretch here. That's okay. It was sort of lopsided, right? It's because this thing isn't a straight line, okay? Since this isn't straight, having it, equal on the epsilon side makes it sort of lopsided on the x side. But that's okay. I picked a delta that was inside right here. So for the proof to work, you just have to say, okay, do this for every epsilon. So if I picked an epsilon that was this big, right, and found the x values, if I picked an epsilon that was really, really tiny, this big, and found it over here, then find another delta for that one. So for every time epsilon gets big or small, right, the closer epsilon gets, right, I can always find a delta that gets closer to the x. And that's how you prove it for every value. If I pick an epsilon, boom, boom, you can find a delta that fits, okay? So how does that work for a proof? Well, if it wasn't true, right? Imagine if I picked the wrong L. For example, what if I picked something up here like B? If I said, B is the limit value for x equals c right here, right? And then you try to come over here. Notice if I pick an epsilon that's small enough up here, then the epsilon would be, the little section would be way over here. It would not include the c anymore. So then your limit would fail, you see. You could not find a delta that contains the distance between x and c. If it's the wrong limit value, or if your function is broken and you have to do it that way, and you have to pick something out here, what will happen is eventually when you get epsilon small enough, it'll be outside and won't contain the x value anymore. So you'll know that you could disprove it that way. Okay? So the function needs to be all connected. It needs to be epsilons that are always around your point, right? So then the proof works. If you have the correct limit value, and it is truly the limit value, then every single epsilon grouping that you pick over here will always encompass the correct x value, and you'll always be able to find a delta size. So that's how the proof works. We'll do it one step at a time. If you pick an epsilon, you should always be able to find a delta for that epsilon, and then you generalize. Oh, but then for every single epsilon, and then it's proven. Okay? So, quick example, not of a whole proof, but of one piece. All right? Let's say that I just want to pick a single epsilon, just so that you can see what's going on here, one step at a time. Okay? Then in a couple of more examples, we'll generalize it to a full proof. So right here, find the limit. All right, we'll do that graphically. Then find a delta such that the distance from the function to that limit value, right, is less than 0.01. In other words, they just gave us an epsilon, right? They gave you the y gap over here of 0.01. That's the size I want to be at this moment, right, to start the whatever process they're doing here. Okay? So they're saying that find a delta such that when this is your epsilon, then the delta encompasses the correct limiting x value, right? So here we go. Right here, the limit as x approaches 3 of 4 minus x over 3. Now, as you can see, this is a linear function, right? X to the 1 has a slope of negative 1/3, an intercept of 4, right? So that's what I have graphed over here. Right here you can see it goes through 4, and then it goes down 1 over 3. Okay? So as x approaches 3, which is right here, the y value also approaches 3. Coincidence. So we're saying that this is 3. Okay? All right. So here's what we do. Now what we're saying is, right here, the absolute value of the function f of x, 4 minus x over 3, minus the limit value, minus 3, is less than 0.01. Okay? So what I'm going to do is I'm going to try to manipulate this into looking like this. So from here, the first thing I can see to do is I can combine the 4 minus 3, right? So I get 1 minus this is less than this, right? Okay. Now what I'm going to do is I'm going to factor out a negative 1/3, like this. Okay, can you see what I did? I took the negative 1/3 out, but when I factored it, right, 1 divided by 1/3 is 3. Check it. If I distribute this back in, negative 1/3 times x is this, and negative 1/3 times negative 3 is this. So it is actually the same thing. Okay? Since this is multiplication, it's okay to split up an absolute value on multiplication. You can do that. So this is where we're at now. I have the absolute value of negative 1/3 times the absolute value of x minus 3 is less than 0.01. All right? Well, the absolute value of negative 1/3 is just 1/3. Right? Multiply both sides by 3 and notice what you get. Like right here. All absolute values are positive, so this is already true that it's greater than 0. And notice this is exactly the statement we wanted. And what this is saying is right here that delta is equal to 0.03. Okay? So notice, since this was the correct limit value, I was easily able to manipulate the epsilon inequality into a delta inequality. And that's how a lot of them will work like that in a proof, except we would do it generically instead of with a number. Okay? So if an epsilon is chosen, all you need to do is find a delta to go with that epsilon. And if you can do that for every epsilon, in other words, if we can do it for just the epsilon symbol generically, then the limit is proven. Okay? So good first example. Good first example. Let's get 2 examples of actually proving a limit using this particular definition in language. So let's start with a linear, right? What I want to do, remember, is prove that for any epsilon chosen from the y range, I can always find a delta encapsulating the x value in the x domain, right? If I can prove that for every epsilon, then the limit is correct and proven. So let's do that. It's saying that the limit as x approaches -2 of 4x plus 5 is equal to -3. So what I want to start with is my function language, right? F of x minus L should be less than epsilon, right? Whatever epsilon distance I want to choose. We're going to be generic this time. So my absolute value of 4x plus 5 minus negative 3 should be less than epsilon. Well, 5 minus negative 3, I can add up to get 8, like so. And notice it's already starting to come together. Since I have the correct limit value, you can see this thing is already ready to factor out the 4. And since the 4 is positive, the absolute value is still 4. And I can do this. Then divide both sides by 4. And I get epsilon divided by 4. So notice what I'm getting here is x minus negative 2 is less than some delta, right? This is the statement that I want right here. And I'm going to choose delta to be epsilon divided by 4. Okay? And if I make this choice right here, then for every epsilon, notice that it's perfect, right? You can pick any epsilon you want. I will then have a delta just by dividing by 4. So, and it works for every epsilon because it's already encapsulating the correct value. If I let epsilon be smaller, then dividing by 4, I'll just get a smaller number. I can divide any number by 4. So you give me an epsilon, I'll divide by 4 and I'll give you a delta. You can make epsilon as small as you want or as big as you want. I will have a delta, and by this string of statements, that delta will always be an interval size encapsulating the negative 2, which comes from the limiting value there. Okay? So if I choose right here, this statement right here, choosing delta equal epsilon over 4, proves that I can find a delta for every epsilon. Therefore, it's proven, right? Do the language here. Therefore, for every epsilon, there exists a delta such that the distance to negative 2 is less than delta. So if that is true, then 4x plus 5 minus negative 3 is less than epsilon. Right? And that's what we're looking for. We're looking for this statement right here. I can find a delta for every epsilon that you try to feed me. If you try to say, I want to get this close to this limiting value, I'll say, okay, I can by getting this close to the x value. And I can do that for every epsilon and delta. Okay, so that proves that this limit is actually the correct value. Let's do something nonlinear, okay? Venturing too far outside of linear, it just becomes a really hefty proof. So I'll just step it up to a quadratic here so that you can get the idea. If you ever have to absolutely prove one of these, of course, we use, series of numbers and infinite things like this and tricks, but I'm just going to show you this one so that you can get the idea that this is actually the language we want to use. But typically, we do limits faster, more efficiently, which you'll see in the next lecture video. But this is important to know how to do. If you ever have to show that this limit is this value, okay, then these are the tactics that you want to approach. So here we go. We want to show that this function, distance to 86, right? 2x squared plus 7x plus 1 minus 86 is less than epsilon. For any epsilon, you pick any epsilon, if this limit is truly correct, then that one should work out, right? Okay. So here we go. I'm going to simplify this. 2x squared plus 7x minus 85 is less than epsilon. Now here's the cool thing. With all these polynomial functions like this, and the way our remainder theorem works, okay, if you need to look that up, I have a lecture video in college algebra if you're interested in remainder theorem. But because of the way our remainder theorem works, if you have the correct limit value here, then what you get as a result here should be factorable. And it should be factorable with the piece that we're interested in, okay? As a matter of fact, this one does factor into this, the absolute value of 2x plus 17 times x minus 5, right? Okay. Now, of course, because of the way, absolute values work with multiplication, I can just say the absolute value of 2x plus 17 times the absolute value of x minus 5 is, of course, less than epsilon, like this. And the x minus 5, that's the piece we're interested in getting, right? That's what we want to show has the delta distance on it. But I've got this other piece, right? Okay, so let's take a little sidebar for a second and look at what we're talking about here on the axis. If you just look at the x-axis, okay, and I've got 5 on there, right? That's the thing I'm trying to approach on the x-axis. If I just step it up and down one step, 4 and 6, right? And if I look at just the values in between here and here, because remember, I'm trying to get close to 5 anyway, right? So there's no need to even look at any other section of the number line. I'm only looking between these two, okay? So look, on the interval where x is between 4 and 6, and notice I'm using an open interval, right? The open interval right here between 4 and 6, if I wanted to, I could say that the delta is 1, by the way, right? Because that would get me a distance to 4 or to 6, okay? So basically, I'm sort of using this as just an easy shell to build off the next step, okay? But on the interval that x is from 4 to 6, okay, then 2x plus 17, if I plug in 4 and I plug in 6 on here, I want you to notice that when I plug in 4, right, 2 times 4 is 8, plus 17 is 25, okay? And I don't even need the absolute value here, look. And right here, if I plug in 6, okay, then 2 times 6 is 12, plus 17 is 29, right? Okay, so what I'm going to do is I'm going to focus in on the bigger picture here, all right? Make sure you follow what I just did. I took the values of 4 and 6, and I plugged them into the piece that I'm not interested in, right? The 2x plus 17, okay? I'm building that right here so that I can show the important piece, and that is just some number value to me, okay? This is the thing that's actually going to be measuring my distance from my center, the x minus 5. So I'm taking the 2x plus 17, and I'm trying to give it just an unimportant numerical value that will serve the purpose of helping me find a delta, okay? So I know I'm going to be at least this close. I could actually get closer, but I'm going to be at least this close here, okay, between 4 and 6. So that means the 2x plus 17 is going to be something between 25 and 29, okay? Well, forget about the less than 25 part. I'm sorry, bigger than 25 part. It's the less than that I'm interested in, right? It's the less than that I'm interested in. 2x plus 17 is less than 29 on this interval, okay? So on this interval, 2x plus 17, and look, if I throw absolute value on there, doesn't matter. It's already positive anyway, right? So on this interval only, which, then the 2x plus 17 will always be less than this output value, right? Okay. So then right here, choose the smaller of either delta equals 1 or delta equals epsilon divided by 29. Okay, now watch. Where did this come from? Let's look at it. I'm saying that the 2x plus 17, right, is less than 29. So imagine there's a 29 over here, right? And I divide it over. That would be epsilon divided by 29, wouldn't it? Okay. But we want to pick a delta for every epsilon, right? Okay. So if I were to pick epsilon big enough, right, it would be so big that this delta may not work anymore, okay, if it was outside of my interval. So that's where this comes in. If it's bigger, then I'll just pick delta equals 1. Obviously it'll work, right, because that's where I built the rest of this off of. Or if I do let epsilon get smaller, then okay, fine, I'll just pick epsilon over 29 as you get closer in, because after you pass the 4 and 6, right, after the x values get closer in, the 1 may not work anymore because it might be too big. But then whatever epsilon they pick, I can still show this inequality. Watch, I'm going to finish it up. So that's where this comes in. So in other words, at this point, I need to employ a little bit of trickiness here, saying, okay, well, if you want to pick a big epsilon, I'm just going to always pick delta equals 1 until you get past the point where that doesn't work anymore. Okay, then I'm showing the 29 as the rest of the piece of the function that's unimportant. And if I just do epsilon divided by 29, then I'll always find a delta that's small enough to fit if you've picked something that's smaller than that gap. Okay, so right here, what I can show is that this right here is equal to this, right? And this is less than 29 times x minus 5, right? And then if I were to let delta right here, I want this to be less than delta. So that would be 29 times epsilon over 29, which is equal to epsilon. So what I've shown here with this statement is this is less than epsilon. That's how the flow goes here, you see? So if x is on the interval from 4 to 6, right? Which is us getting close to 5, then this has to be true. This is going to be less than 29. And I've just shown that this is less than the delta right here. Therefore, this is less than delta when f of x minus 86 is less than epsilon. Right? Or maybe some better language for that would be thus, if this is true, then. And that's really the way you want to say it. Because if this is true, then I can say this last step right here is true. Okay? Is equal to that. Really, this is still a little bit of hand waving. This isn't like a proof that I would 100% publish or anything. I'm just trying to get you the idea of the language of the precise definition of limits here. Okay? And to give you a small taste of what you would need to go through on any given function if you actually had to 100% prove one of these limits. Also, if you do happen to carry on, we hit this definition again in multivariable calculus on a much grander scale, and it actually becomes a little bit more important to do then. So don't just let all this slip away. All right. So I hope this has helped you understand the precise definition of limits.